Okay, welcome to the introductory section of this course. We were covering the introduction, and this is a third part of the introduction of this course. We have already discussed the metric SI units. So metric SI units, the concepts such as system, state postulate, equilibrium, process and process path. We already defined intensive, which essentially is not dependent on the size or the system volume, and extensive, which depends on the mass volume. So the example of intensive is temperature, pressure, and extensive would be like volume itself, right, a mass. And then we have defined density, specific gravity and specific weight. You can turn any extensive variable to intensive variable by dividing with mass or volume. Now in this part of lecture, we are going to discuss the temperature scale and discuss the pressure and how to measure such pressure or pressure differences using barometer and manometer. So let's start with the temperature. When you talk about temperature, the only thing which you think of is the feel of the hotness or coldness of an object. But defining a value to that is extremely difficult, right? You can make mistakes. For example, at a room temperature, you can touch a steel material, you can feel that it's colder than another material such as wood in the same system. So just based on your sensation or feeling, you are not going to, it's difficult to define a value to it. So, but you are aware from your natural environment or instinct that when you put a object, a hot object on top of a cold object, eventually both the objects turn out to have the same sensation in some sense. Or in other words, you know that temperature decreases if you keep a hot coffee on a table at room temperature. So there is a heat transfer from a high temperature, so called the feeling based high temperature, to a low temperature. So this is very well defined in the zeroth law of thermodynamics. So let's take an example. So you have, what you have done is you have taken an iron object which is at 150 degrees Celsius, put on top of a copper object which is 20 degrees Celsius, and you have isolated it. This is isolated in some sense. Okay. After a while, you see that both reaches a certain temperature. Now this is, we call it that the both bodies, that is two bodies reaching the thermal equilibrium. Same temperature stands for thermal equilibrium. So this leads to a zeroth law of thermodynamics, which says that if your two bodies are in thermal equilibrium with a third body, then they are also in thermal equilibrium with each other. So you can take, for example, A with B and A with C. If both systems are at thermal equilibrium, this will imply that B and C are at thermal equilibrium, and B and C, or in this case particularly A, could be a thermometer. For example, you can measure a thermometer, get the same temperature. You can measure another system, you get the same temperature, which essentially means system 1 and 2 are at equilibrium. So this is what the second statement says, that by replacing the third body with a thermometer, the zeroth law can be restated as two bodies are in thermal equilibrium if both have the same temperature reading, even if they are not in contact. So this is the field-based concept, okay? But we'll discuss a little more that how do you define the scales, and this was actually a challenge in earlier age. Like they came up with the system such that this can be reproduced, every time you can reproduce the same kind of systems or same kind of references, so called. So naturally the content or the fluid we considered was water because it was available for sure. So all temperature scales, so there are many temperature scales available. They are based on some easily reproducible states. So the commonly is freezing and boiling point, okay, at atmospheric pressure, okay. Now they are defined as ice point and steam point. So let's look at what is ice point. Ice point is nothing but a mixture of ice and water that is in equilibrium with air, okay, saturated with vapor at 1 atmosphere. So at this condition you have air as well as you have water vapor, because you are conducting this experiment at certain conditions which is open to air, okay. And then you have this steam point, which is a mixture of liquid water and water vapor with no air. So for ice we have defined something called 0 Celsius and 32 Fahrenheit. These are the two different units which are used, okay. Celsius is a scale which is more of SI unit, and Fahrenheit is an English unit, okay. And then the other point, which is a much higher temperature, is a steam point. So steam point is 100 degrees Celsius or 212 degrees Fahrenheit. So these are the two scales which are based on this reproducible state, based on water, okay. But then it depends on the fluid which you are using, and the idea was not to just stick to a fluid, should be independent, and that came up the idea with thermodynamic temperature scale, which is independent of any fluid which we used. And the two scales which came up, which we have designed by people, are Kelvin scale, which is SI, and Rankine scale, which is English. So let's look at it, how it can be related. You know very well that Kelvin is related, temperature scale in Kelvin is related to Celsius, and by this relation, which is temperature of any Kelvin unit is Celsius plus 273.15, and then you have this Rankine, and the Rankine and the Kelvin there is a ratio 1.8, so that temperature of any in Rankine scale is just 1.8 times the temperature in the Kelvin scales. The difference here is same for the Kelvin and Celsius, and that is true for the Rankine and Fahrenheit. So that means the English and the SI units are more or less made in a similar line. Okay, there is one difference here, that earlier when it was designed, the Kelvin scale, it was based on the ice point 273.15. That means when the ice is formed. But later on they found that the more precisely reproducible state is a triple point, which is 273.16, and that's where the value is assigned. And that's why you can see here the scale of this corresponds to this here. But once you have done that, you cannot change the Celsius, so the definition is still same. That's why it's 0.01 degrees Celsius corresponds to 273.16 Kelvin. Okay. Alright, so the other unit which we are going to use, so we are talking about intensive variables, which are extremely useful, right? So we talked about that you can define state of an incompressible fluid by providing two intensive variables. Okay, for single phase, temperature is pressure is fine, but for or you can use temperature and specific volume. Specific volume is variable even if it is there is a phase change, such as water going from the liquid to the vapor, but the pressure is dependent on the temperature when there is a phase change. So we talked about that. So pressure is extremely useful unit for our thermodynamic analysis. It's a simple definition. It's a normal force per unit area. It's commonly used for gas and liquid. For the case of solid, we use stress. Now, is pressure is a scalar or vector? We will say the pressure is a scalar for simple reason that you have already taken the directional force. You are saying normal or tangential, so that makes it that the direction is already incorporated. On the other hand, stress is not. Stress your stress turns out to be tensorial continuity. So now pressure unit is 1 Newton per meter square in SI unit. We also can say in terms of Pascal. This is a unit for Pascal. This is a small value, typically which we encounter in daily life is quite large, such as 10 to the power 5 Pascal, bar or atmosphere. So the commonly used units are bar, atmosphere, and this kilogram force per centimeter square. This is quite useful in different countries such as Europe. They use it quite often. Here nothing but is like 1 kilogram force, which essentially means you have fixed the mass by 1 kg, and the g is 9.807, and hence you have this specific value. You can clearly calculate the pressure acting on our feet by knowing simple relations here. So you have the weight, and you can clearly see based on this analysis that a pressure for this person acting here is around 22.23 kilopascal. So this is your mass, your g, and the area of the feet. We are assuming the area of the feet for this person and a chubby person is same. Okay, that's an assumption. So considering that this person is experienced twice the amount of pressure on his feet, so that is analysis. You can do that. Pressure, when you measure like pressure of your tire, you measure with respect to atmosphere. That we know that. I mean, that's why always we measure in terms of something called gauge pressure. But let's look at absolute pressure first. So which is basically pressure at a given position. It's measured relative to the absolute value. So what does it mean? That you have no gas, nothing in a container, and that gives you a vacuum, and there is no molecules which are imparting any pressure on the container of it and leading to the pressure we can refer as a vacuum pressure, which is this 0. So you have this absolute pressure, vacuum pressure is 0, and then you have this, let's say, this pressure which you desire. So this becomes a pressure, again this is absolute, okay, and this is the value here, and this is the, let's say, atmospheric pressure. So the difference with respect to atmospheric pressure is called gauge pressure. So this is the one. So gauge pressure is nothing but P absolute minus P atmosphere. So many gauge pressure measurement units are referred in this form. They are actually tuned or calibrated such that the reference point becomes the atmospheric pressure, and whatever the difference is the gauge pressure. And the vacuum pressure is the pressure below the atmosphere. So in this case, for example, you have this P atmosphere which is larger than the actual or the absolute value of pressure, and hence the difference gives you the vacuum pressure. Okay, so these are the two meaning of that. Okay, so let's now look at the variation of the pressure. So you can take a rectangular element which is defined in this one. So this is our rectangular element, okay, and the shaded blue region is the fluid. Now you can do a force balance in the horizontal direction. The horizontal direction, you can do the force balance. You can clearly see that the pressure should be same at each point. So let's just we'll do a force balance in the vertical direction. So the vertical direction, you have the pressure. Let's say you are defined pressure at this point P2, okay, which is acting on this element of the fluid, and the weight of the fluid is W, okay, and then the pressure acting on the other side of the fluid is P1. So if you do a force balance, you know that the P2, or in this case the P1 times the cross-sectional area will be the force. Now the cross-sectional area would be your this delta x, okay, and the y direction which is perpendicular to this plane, okay. So that becomes your force acting on the fluid from bottom. And then you have this another term which is here, which is basically we multiply by delta x delta y. So that becomes the force acting here. So this could be your F2, for example, okay. And then the weight is downward, so you have to look into the weight. So you have rho g, and this is the volume here. So this must be 0 because it has to be balanced. Okay, then you can do the mathematics here because this will cancel out. So what remains is P2 minus P1, which is equal to minus rho g delta z. So it tells you that P2 is smaller than P1 because rho is positive, g is positive, and we have considered delta z to be positive. In other words, you can say that rho P below is P above plus rho g, absolute value of delta z. Okay, so that's what we know that typical gauge pressure or the pressure will look like in this form, in a linear form, so which essentially you can understand that this fluid here is balancing the weight of the other fluid, and hence the pressure should be more. Alright, so that's what we say, the pressure of a fluid at rest increases with depth as a result of added weight. Now the pressure variation depends on the fluid density. So you consider this particular room, you are asking the pressure somewhere up top here and below, which is separated by a few meters. The pressure would be the difference would be extremely small, and the reason is the density of the air is very small. So on the other hand, that is not true for liquid, so because the density is quite high, so we have to consider the variations in the pressure. So this is an example. So this is a container containing a fluid. At the top of the layer of the fluid, the pressure is given as P atmosphere because it is open to the atmosphere, and somewhere in the fluid, let's say 2, the pressure is simply given by P atmosphere plus rho gh. Okay, if the density is variable, okay, then you have to consider in the differential form, because recall that in the previous one we talked about P2 minus P1 is equal to minus rho g delta z. So this is nothing but delta P by delta z, and then if the delta z goes to rho g. So you can find out the delta P by integrating this expression, and that's what this is given here. Okay, so let's look at some examples like what implication of the pressure. We talked about the pressure along the horizontal plane for a given fluid should be same. Okay, the variations are only when you move along the vertical plane. Okay, so this is a very nice illustration. So here you have water and mercury in a container, which is a very unusual geometry, and you can clearly point out that the pressure at A, B, C, D, E, F and G points should be same, and the reason is they are at the same horizontal plane. But H and I pressure here is not same as, they are not same, and the reason is, though it's at the same horizontal plane, but they have a different fluid, so they contain different fluid, and hence you have to make use of the differences in the density we'll talk about later. Okay, so that means the pressure is the same at all points on a horizontal plane in a given fluid regardless of the geometry, provided that the points are interconnected by the same fluid. So it's extremely important that they should be having same fluid. Okay, and it has a many repercussion. This statement has a many repercussions. One of the repercussions is a Pascal's law, which is originated from there. So it says that if you apply a pressure to a confined fluid, it increases the pressure throughout by the same amount, and its application is in hydraulic jack. This is just one example. So based on this, you can lift a large weight by a small force. So let's look at it, how it does. So you consider this jack in this schematic diagram. You have a single fluid here, which is represented by this color, and you apply a force F1 at this end. This leads to a certain pressure, let's say P1. Now once the pressure is, this system is equilibrated, we are assuming that it's a quasi equilibrium state, the pressure P1 should be same as pressure at P2, because they are at same horizontal level. So now what about the force F2? So you can look at it, P1 is equal to P2, you can find out the forces, and it essentially means you can come up with this expression, F2 by F1. Now F2 by F1, is it greater than 1 or less than 1? Since A2 is much larger than A1, it means this is much larger than 1. Essentially you have increased the force by many times, and that's the reason that you can lift a big car by applying a small force there. So it has a wide applications, and this ratio A2 by A1 is also called ideal mechanical advantage of the hydraulic lift. So how do you measure pressure? And so you can measure atmospheric pressure, and this was the first time was done by Italian scientist, and that's what the name come up. So I will talk about this. So let's take a look how it is done. So you take a tube of let's say mercury and invert it in a containing mercury. So what happens is, so you have such a situation finally, and you have 2 points. Let's say you have point B. So what is the pressure at B? It's going to be atmospheric pressure, because this container is open to atmosphere, and at the end of the tube there is a small vacuum, or even if it is a vapor, is so small in volume and light that you can still consider to be vacuum. So this pressure here is going to be 0, and this pressure here is going to be atmosphere. Now you can do a force balance, okay, and if you do a force balance, you will come up with this expression that P atmosphere is nothing but rho g h, where h is the height of the mercury from the top of the container's mercury level. So this is a way we calculate atmospheric pressure, and this equipment or device is called barometer. So standard atmosphere is 760 mm Hg at 0 degrees Celsius. So 760 mm Hg is 1 atmosphere, and the reason for that is at 1 atmosphere 760 mm of Hg is raised. That means H is basically is 760 mm. Okay, but this is at 0 degrees Celsius, and this is also called, is equivalent to 760 torr, and torr is basically named after the Italian scientist. The name is Torricelli. So let me just write it. So this is named after the Italian scientist. Now using this force balance, you can clearly see or clearly make out that there is no effect of the geometry of the tube. If you increase the width, if you increase the height of the tube itself, it's not going to affect. So the length and cross-sectional area have no effect on the height. If it is 1 atmosphere, you're going to get 760 mm Hg, irrespective of whatever tube you're going to use. Okay, so this is an illustration which clearly says that. Okay, so let's apply a little bit more on the pressure. Now if you are interested to, let's say if you take a container of the gas and you want to find out the pressure of the container which contains gas, then how do you do that? You can apply a simple manometer, and this is an illustration. So you have a gas and you are attaching to this tube containing a fluid. This fluid could be anything. It could be mercury, it could be water, alcohol, oil. okay, and you are interested to find out the pressure here, let's say pressure here, okay, P. Now since it's a gas and you know that the gas density is quite low, you can assume that the pressure here is same as pressure here at P1, okay. Now because of the mechanical equilibrium, the pressure here in this fluid, the gas should be same as in mercury or whatever the fluid we are using, right. So and now because of the fact that the horizontal plane should be same, the pressure should be same as P2. So P2 should be at P1. So essentially you can connect this P2 to P atmosphere, which is open here, and you can come up with the expression. So the P2 is nothing but P atmosphere plus the density of the fluid which you are going to use, and G, and this height of this. So this is simply rho GH, right. So this is the basic manometer usage. In many cases, in many industrial applications, other applications, there are many fluids which are stacked up, these fluids are typically immiscible fluids, okay, and you can make use of these fluids in manometer as well. So how do you do that? You have to remember two things. One is of course that the delta P pressure change in a fluid is simply rho GH for a continuous fluid, same fluid, and P below is greater than P above, okay, by rho GH. Okay, so let's look at it. So in this case you have three fluids, and you want to find out the pressure at bottom one, that is represented by 1 here. So you take pressure at the top and add up the different contributions. This comes from rho 1 G H1, this is rho T G H2, and this is rho 3 G H2. Okay, these are different pressure differences from this point to this point, this point to this point, and so on, and that's what you're going to get the pressure at 1. Okay, you can make use of this in a flow, and that's where it becomes quite useful in many devices, such as a valve. What is the pressure drop across the valve, or for that matter pump? You can make use of similar kind of devices to calculate the pressure drop. So one device for that is differential manometer. Okay, so you have a fluid and you are interested to find out the delta P between these 2 points. Okay, there is a flow, that means there is a pressure gradient. Okay, so now so here is the fluid, okay, and you are assuming that the density remains the same at here, and so this is A point, this is here B point. So the pressure at A should be same as pressure at B. Okay, and so that means let me just start writing here. So this is your P1. The first you have to do is find out the pressure here at A, which is nothing but P1 plus rho G A plus H, because this is the height which you are talking about from here. This is A plus H. So pressure here for the same fluid is nothing but P1 plus rho GH. So this is your P at A. Then this is same as P B, and then is going up. So you have to decrease it. So that means rho 2 GH is this part, and then you have this rho 1 GA. Okay, and that's how you're going to achieve P2. Okay, so if you do this analysis, you the value or the change in the pressure turns out to be simply rho 2 minus rho 1 multiplied by GH. Okay, so we can end this lecture by doing an example, and this is an example. So you have a piece of experimental apparatus as shown in the figure, where air is passing, and we are using G is equal to 9.5, and the temperature is 5 degrees Celsius. Air flow through inside the apparatus, and there is an orifice. This is your orifice. Okay, and we want to find out the pressure drop across the orifice. Okay, so what do? You apply a differential manometer with mercury as a fluid. So this is the differential manometer, and what is shown is the density here is given for the manometer, and the height difference. So when you apply this, you observe height difference. Height difference represent there is a pressure drop. So the height difference, which means this here, is given as 200 millimeter. So what is the pressure drop? So we talked about there that this is, let's say, 1, this is 2, okay. So P1 minus P2 is going to be rho 2, which is the density of the mercury, minus rho 1, which is density of the gas, multiplied by G and H, okay. Now in this case density of gas is close to 1.2, okay, kg per meter cube, you know. Density of mercury is quite large, so we can ignore and consider this to be simply the mercury density multiplied by H, okay, and that's how we're going to plug in the values, and we can get the value which is 25.84 kilopascal. So in this course we essentially are going to follow a certain pattern, that you have been given a problem, and so that would be a problem statement, okay, and there has to be a you can come up with the schematic diagram of the problem which will allow you to solve the problem more efficiently. That means a schematic will be given, or you can come up with the schematic. We will start with the assumption approximation. Just like in the previous example, we assumed that the density of the air is smaller than the mercury, and then we apply the laws, calculate, use the properties, calculate whatever the values you are desired to do that, and provide the reasoning and discussions. So this is a format which will allow you to solve any problem more efficiently and illustratively. Okay, so with this I think end this lecture. I'll go through this summary again when I'm going to start the next lecture.